This is the recorded lecture for, it's the last one for chapter 2A slides, and we have been, where we left off was we learned about ionic and covalent bonds. Now we're going to learn about hydrogen bonds, which are a little bit different from the other type of chemical bonds because they're not bonds that hold atoms together to form molecules. They are bonds between molecules. So they're called intramolecular bonds. And the way it works is, and this is a good animation, by the way. Let me find out which slide this is because this is really good for you to watch. I encourage you to watch this. It is from slide 63, the animation on hydrogen bonding. And then if you look on slide 64, you see images of water molecules. And there's a few things. First of all, each water molecule is chemically bonded or hydrogen bonded to the other water molecule. This explains why we see water forming droplets on your car windshield, for example. And also, if you notice, each water molecule is lined up in such a way that the oxygen end of one molecule is facing the hydrogen end of the other. And that is due to the fact that water is polar. The oxygen end has a slightly negative charge compared to the hydrogen end, which is slightly positive. So the oxygen end, which is more electronegative, is lined up to face the hydrogen end. And you can see that with all of these water molecules. So that's what we're looking at is hydrogen bonding. And hydrogen bonding explains, for example, insects that can walk on the surface of a body of water. And there are other chemical properties of water as well that are important, such as cohesion and adhesion. The fact that ice floats on liquid water, that's usually not the case. The solid form of a substance typically sinks in the liquid form. So there are different properties of water, but we're going to move on to section 2.5, chemical reactions. In chemical reactions, you see a representation of the chemical formulas of the reactants, which are the substances that enter into the reaction together, and then the products that are formed after the reactants are, their chemical bonds are formed, rearranged, or broken. And how they're represented is with a chemical equation. So before we look at equations, let's look at chemical formulas or molecular formulas. For example, H2O stands for 2 atoms of hydrogen and 1 atom of oxygen. And that's, of course, the molecular formula for water. And the molecular formula for glucose is also shown. C6H12O6 means there are 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen in one molecule of glucose. Excuse me. And I was looking to see if there was an example of a chemical reaction so I could show you other things, but I don't see a good one. Oh, here's one. Okay, so this is an example of a chemical reaction, and then we'll go back to the notes that we missed. This is showing glucose plus 6 molecules of oxygen react to form 6 molecules of carbon dioxide plus 6 molecules of water plus ATP. This is the chemical equation for cellular respiration, which occurs in our cells, in the mitochondria of our cells. And glucose is broken down in the presence of oxygen into carbon dioxide and water, and energy in the form of ATP is extracted when that happens. So, going back, The types of chemical reactions include synthesis reactions. For example, when amino acids are joined to form proteins. And synthesis reactions are also known as dehydration reactions. Then we have decomposition or hydrolysis reactions, and they involve breakdown. So an example of a hydrolysis reaction or decomposition, glycogen, which is the storage form of glucose in our liver cells and our muscle cells. Glycogen is just long chains of glucose, and those chains can be branches. It can form branches as well. Glycogen is also known as animal starch, but it is the storage form of glucose in our liver cells and our muscle cells. When glycogen is broken down to release those individual glucose molecules, those monomers, glycogen is a polymer and glucose, the individual glucose molecules are monomers. When that happens, this is a hydrolysis reaction. And then we have exchange reactions in which certain atoms will just exchange places. And we also have oxidation reduction reactions or redox reactions. Cellular respiration is an example of a redox reaction. In redox reactions, one of the reactants is oxidized and one of the reactants is reduced. I always teach my students the word oil rig, and I'm not even going to try to handwrite it, but I am going to insert a text box and just write it out for you. Oil rig. And that means oxidation is loss, reduction is gain. Oxidation is loss of electrons, reduction is gain of electrons. Excuse me. Okay, oxidation is loss of electrons. Reduction is gain of electrons. Now, how do we look at a chemical equation and tell what has lost electrons and what has gained electrons? Well, you have to remember that there are electrons found in these hydrogen atoms. So really, when I look at glucose and see that it's got 12 hydrogen atoms, and then I come over here when it forms into carbon dioxide, it has lost all of those hydrogen atoms. Then it has lost electrons. It's lost the electrons that are attached or that are that come along with those hydrogen atoms. So when I see that a substance has lost hydrogen atoms, that one is oxidized. So glucose is oxidized into carbon dioxide. And then the other reactant, oxygen, gains those hydrogen atoms and becomes water. So reduction is gain of electrons in the form of hydrogen atoms. So it is the oxygen that is reduced. Chemical reactions can be exergonic, meaning that they release energy, and our catabolic reactions or breakdown reactions are exergonic. And then endergonic reactions are the anabolic reactions or the synthesis reactions. These reactions build larger molecules. Then there are reactions that are reversible. And there's a little bit of information on the speed or the rate of chemical reactions. Higher temperature typically will increase the rate of reaction unless the temperature, there is a maximum. If the temperature rises too high, then it destroys the molecules. But up to a certain point, increased temperature will increase the rate of a chemical reaction. It will speed it up. When the concentration of the reactants is increased, that will increase the rate of reaction up to a certain point, and then it won't have any effect anymore. And then the smaller the particle sizes, like for example, when we chew up our food, they're going to react and digest more quickly. than if we swallow our food whole. Catalyst in the body, typically enzymes are the catalyst. Enzymes are biological catalysts that are almost always proteins. So biological catalysts that are proteins. And enzymes will also speed up the rate of chemical reactions. Now we're going to move on to Chapter 2B. And we're going to learn about biochemistry, which is the study of the chemical composition and the reactions of living things. The chemistry of living things, basically. We start out by classifying all chemicals either as inorganic or organic. If they are organic, they are going to contain carbon and hydrogen. And that is not in the notes, so you need to add it. Organic compounds are defined as compounds which contain carbon and hydrogen together. Inorganic compounds can contain carbon. This is a mistake, and I am sorry, but that is wrong to say that. So we're going to mark through it. Because carbon dioxide, or CO2, is inorganic. CO2 does not also have hydrogen in it. So make sure you know if it's organic, it contains carbon. It contains carbon and it contains hydrogen. It's got to contain both of them in the same molecule. There. Organic contains both carbon and hydrogen atoms together in the same compound or molecule, whereas inorganic usually doesn't contain carbon, but it can, as long as it doesn't also have hydrogen. So inorganic compounds are water, salts, many acids and bases, like hydrochloric acid is an inorganic compound. Sodium hydroxide is a base that's an inorganic compound. But the organic compounds that we are most concerned with are carbohydrates, fats or lipids, proteins, and nucleic acids. Our most abundant inorganic compound is water. It accounts for 60 to 80% of the volume of living cells. It varies based on how dehydrated you are or how hydrated you are. But it is the most important inorganic compound because of its properties. And these are the properties that go along with the fact that water is polar. It's a polar covalent molecule, and it's capable of forming hydrogen bonds. So water has a high heat capacity, a high heat of vaporization. It has solvent properties for polar molecules and ionic compounds. The only things that won't dissolve in water are non-polar covalent molecules, like lipids, which are fats and oils. Water is highly reactive, has a high reactivity, and water acts as cushioning in our cells, in our tissues. So high heat capacity means that water has the ability to absorb and release heat with little temperature change, and that prevents sudden changes in temperature. It helps us to maintain body temperature. So in other words, water does not change temperature quickly when you try to heat it up. You may notice that when you have tried to boil water on the stove. Water has a high heat of vaporization. That means that it requires a large amount of heat or large amount of energy for water to evaporate. And that is useful as a cooling mechanism. for example, when we sweat and the heat evaporates along with the water. Water is a solvent. It's a polar solvent. That means that it can dissolve ionic compounds and also polar compounds, like glucose, for example, or sugar. This shows you how salt dissolves in water. Water will form a hydration sphere around the sodium ions and the chloride ions. The hydrogen end of the water molecule, that because it's slightly positive, will face the negative chloride ions and form a sphere around it. And then the oxygen end will face the sodium ions and form a sphere. So it will isolate those sodium and chloride ions from one another. Water is also highly reactive. It is a component of hydrolysis and dehydration reactions. Remember, hydrolysis is our breakdown reactions. Dehydration reactions are our synthesis or building reactions. And water is a cushioning agent. For example, cerebrospinal fluid, or CSF, cushions our brain and our spinal cord. And we will stop here, and our next recording will begin with salts.